Hey everybody. For the next week and a half, we are going to be talking about work, energy, power, and momentum. Okay, there's a lot of stuff we're going to cover in the next week and a half, which usually it takes me 2 weeks to cover. So I've condensed a bunch of things, we're skipping a few things, and it also means that we're going to start moving a little bit faster. And that means that I'm also not going to always solve every single algebra step in the problems that I'm solving. And I'm also not going to always put values in and give you what the correct answer should be for the problem that I'm working through. One of the prereqs for this class is algebra. And so I'm going to let that be up to you if you're confused about some algebra stuff that I kind of went through pretty quickly to come to me and ask me about that, okay? And so with that, we are going to start our study of work and energy. We've already seen work a little bit in lab. Work is the application of a force which moves an object over some distance. Only the component of the force in the direction of the displacement or in the direction of motion is the component that's doing the work, okay? So the work done is equal to, we're going to say the force parallel to our direction of motion times our displacement. And that equals FD cosine theta. And so this is the work done by a constant force F at an angle theta to our displacement D. So here's an example. We've got someone who's in this little bicycle thing, and we've got this big parachute here. The parachute collects the wind, and that wind is applying a force to that parachute, and then there's a tension force here, and so we are getting the wind applying a forward force on this person at some angle with respect to the horizontal, okay? And so that vector of force is pointing off in this direction. So if we come over here, we've got that vector of force. We want the force component that's parallel to our displacement, parallel to our direction of motion. And so if this angle was theta, then this side, the force component that's parallel to our direction of motion, is adjacent to our angle theta. And if we're adjacent, then we use cosine. And so that parallel component of the force is equal to F cosine theta. So that's our work. Force parallel times our displacement, FD cosine theta. The unit of work is what we call a joule. This is also the same unit that we're going to use for energy. And here is a joule, Joule, and named for a person with the last name of Joule. And we abbreviate it with a capital J. 1 joule is the same thing as 1 Newton times meter, okay? And so since Newton is a Newton is a kilogram meter over seconds squared, then that means 1 joule is a kilogram meter over seconds squared times meter. So 1 joule is a kilogram meter squared over seconds squared. And so here we have another example of someone doing work. Work is, our FD cosine theta. This person is applying a force downward on the edge of this lawnmower, okay? So the work that this person does on the lawnmower is equal to the force applied times the displacement times cosine theta. And so here theta is the angle between our force and our displacement. Work is done on a system by external forces, forces that come from outside of the system. So in this example here, we've got someone who is a windsurfer. Okay, so the system is the person on their wind surfboard, okay? And then they're on the water. There's a force being applied to the sail here from the wind. That's our external force. Initially, that person has zero velocity, but that force is being applied. And as that force is applied over some displacement, they gain speed. And at some later distance away from where we initially started our problem, that person will have gained speed. The system's kinetic energy, that's energy associated with motion, increases as this force is applied, as work is done on the system, and our windsurfer speeds up. Here are some more examples of work. We've got a block here, and we have some initial velocity. Then we're applying a force over a displacement, and at some later time, because we've been applying that force, we've been doing work. The velocity is larger at a later time, as after we've been applying this force for some distance, after we've been doing work, okay? So the angle between our force and our displacement is 0. They're parallel to each other. So our work is just going to be the force times the distance, because our angle is 0 degrees, cosine of 0 is just 1, okay? And then we come down here, we are applying our force. We're pulling on this block with some rope. We're applying our force at some angle above the horizontal, okay? And as we're doing that, we're applying our force over some displacement. And our work in this case then is equal to FD cosine theta. Whatever this angle is between our force and our displacement, we have to multiply that by our force times our displacement. So FD cosine theta. Even more examples. Okay, so here, imagine I'm a person holding a suitcase, and I'm exerting a force on the suitcase. That's this force here. But I'm going to take a path, a displacement that takes me up these stairs. Okay, so as I do that, my force is up, but my displacement is up the stairs. So there's an angle between the force that I'm applying on the suitcase and my displacement. So then the work that I do is FD, and whatever this angle here is, FD cosine theta. Now I have my suitcase connected to a rope. That rope is connected to a motor, okay? So there's a tension force in that cable right here, okay? That tension force is pulling upward on the suitcase. But my displacement is going down. So really what's happening is that the motor is slowly letting the suitcase displace downward. So we're slowly dropping our suitcase downward, but we still have this upward force here, the tension force that's on the rope, okay? But our displacement is downward. So if we're thinking about the work that we're doing, we've got the force, which is the tension on the rope here, times our displacement. We're moving downward. This is our direction down. Cosine theta. So this time our angle theta, our angle between our applied force and our displacement are opposite of each other. That means that the angle between my displacement and my force is 180 degrees. Cosine of 180 degrees is -1. So in this case, my work is FD times cosine 180. So that's negative force times the displacement. And so that's going to equal minus FD. So in this case, we're actually doing a negative amount of work by letting our suitcase, in this case, fall to the ground, or slowly lowering the suitcase to the ground, let's say. Here, I'm applying a force upward again on my suitcase, but I'm not moving through any displacement. If work is FD cosine theta and D is 0, then you're doing no work. And over here, also interesting, we're doing no work, even though I'm pulling upward with my force, but I'm moving forward. Why am I not doing any work on the system in this case? Well, remember, work is FD cosine theta, or it's our displacement times the component of my force parallel to my displacement. If I'm moving horizontally, but my force is directly upward, okay, there's no component of that force parallel to my direction of motion. So in this case, if I look at FD cosine theta, the angle between my displacement and my force, I'm pulling upward, my arm is exerting a force upward on the suitcase, the angle between the displacement and the force is 90 degrees. Cosine of 90 degrees is 0. In this case, I've got F, my force. I am moving through some displacement, but cosine of my angle is 90 degrees. cosine of 90 is 0. So even in this case, we're doing no work on the system either. Now that we've gone through some examples, simple examples for work, I'm going to have you think about this conceptual problem here for your engagement check. We have a block and it's moving to the right in the positive x direction through a displacement delta x while under the influence of a force with the same magnitude F. What is the correct order of the amount of work done by the force F from most positive to least positive? So we have 4 blocks labeled A, B, C, and D. They all have a force of the same magnitude being applied to them, just, in different angles, okay? But all of them are also moving to the right. So the displacement for every block is to the right, and you see the vector of the force here. So synthesizing everything that we just talked about, could you rank from most positive to most negative the order of the amount of work being done on all 4 of these blocks? Now we're going to apply this idea of work, finally, with some numerical values.
We are going to walk through a couple of examples of how to compute work. And a lot of these problems, at least these first 2 I'm going to work through, are going to look really similar to problems we've already done when we were talking about Newton's second law and forces. So we have a person who is pulling a 50 kilogram sled for 5 meters, so we'll say the distance is 5 meters, on snow with the coefficient of kinetic friction of 0.2. Initially, the person pulls the sled with a force, we'll call that force applied, of 120 newtons. And so, if our sled is being pulled at an angle of 0 degrees, find the work done on the sled by friction and the net work. So work done by friction and net work. Okay, and so we're going to figure out how to calculate those. Well, I wrote down all of my knowns. These are my unknowns, okay? And I've got my box here. Let's draw the free body diagram. So we've got the weight of the object down, its mass times gravity. We've got the normal force pointing up. We've got the force of friction opposing our motion. And then we're pulling horizontally. This is my applied force. Or you might also call it tension, the tension force, because we'll assume we're pulling on it with some cord or string or rope or something, okay? So how do we calculate the net work and the work done by friction? Well, first let's think about the work done by friction. Okay, so if we use our equation for friction, work done by friction in this case, is it going to equal our force? So in this case, that's the force of kinetic friction times the distance over which this force is applied times cosine theta, where this theta angle is always the angle between your direction of motion, we'll assume that we're moving forward, and the angle at which the force is applied. So this angle is the angle between our direction of motion and the direction in which our force is applied. So in this case, our direction of motion is this way. Our force is applied 180 degrees opposite that. So this is going to equal our kinetic friction times the distance pulled times cosine of 180 degrees. Okay? Cosine of 180 degrees is -1. So the work that friction does is going to be a negative value. Okay, the work that friction does is essentially removing energy from the system. So remember, our force of kinetic friction is always going to be our coefficient of kinetic friction times the normal force. And then here we times our distance, and our cosine of 180, that's -1. So actually this whole expression has a minus sign. So this work done by friction is opposite our direction of motion. That's why we've got this minus sign here. Then how do we find this normal force? Well, you can always go and apply Newton's second law in the vertical direction in order to figure out what your normal force is. So if we do that, if we do Newton's second law in the vertical direction, equal to mass times our acceleration in the y direction. We are not accelerating vertically at all, okay? So then that quantity is 0, okay? And then in the y direction, we've got normal force upward, and then we've got our weight downward. So the left-hand side of this equation is the normal force minus our mass times gravity. So then we just proved to ourselves that the normal force is equal to our mass times gravity. So then we can come here and plug in mass times gravity for our normal force. So this is equal to minus mu k times mass times gravity times the distance that we pull, okay? And then that is equal to minus 0.2. That's our coefficient of kinetic friction times our mass, 50 kilograms, times 9.8 meters per second squared, times the distance we pull, which was 5 meters, okay? And then that gives us the work done by friction, which is minus 490 joules, okay? Because remember, our unit for work is units of joules, okay? And so that's how we could find the work done by friction. And now, so we've got that equals minus 490 joules. Now, what is the net work, the total work done in this problem? Because we only calculated the work that friction does. Our net work will then be equal to the work done by friction plus the work done by the person pulling the sled. So we'll call it the work done by the applied force, by the person pulling here. We already calculated the work done by friction. That's this work right here. So that's minus 490 joules. Plus, our work applied is going to be the force applied times the distance over which we pull it times cosine of the angle between our direction of motion and the direction of the applied force. And in this case, the direction of motion and the direction of the applied force are in the same direction. That angle between them is 0, and cosine of 0 is just 1, okay? So then this is equal to minus 490 joules plus our applied force, which we're told that, let's see exactly what it says. Person pulls on the sled with a force of 120 newtons. That's our applied force. And we are pulling it 5 meters with that applied force. So minus 490 joules plus 120 times 5 will give us a total net work of 110 joules that we do on the system. Now we're going to repeat this calculation, but this time we are going to apply our force at an angle of 30 degrees with respect to the horizontal, okay? So on our free body diagram, we still have the weight of the object down. We've got our friction force opposite the direction of motion. We've got our normal force pointing upward from the surface. And this time, we're pulling at an angle of 30 degrees from the horizontal. So our applied force is still equal to 120 newtons, but this time at an angle, okay? And our mass, distance, coefficient of friction are still the same, okay? How is this going to change the outcome for the calculations we want to find? We still want to find the work done by friction and the total work, or the net work. Okay, so let's repeat our calculation for the work done by friction. This time, though, we're pulling with the applied force at the angle, okay? So our work done by friction is going to equal the force of friction, the force of kinetic friction, times the distance over which that force is applied, times cosine theta. Theta is the angle between our direction of motion and our applied force. So this angle is going to be 180 degrees for our friction force. Cosine of 180 degrees we saw was minus 1 earlier. Okay, so this is equal to minus, remember, our force of kinetic friction is always equal to the coefficient of kinetic friction times the normal force, okay? So we've got minus mu k times the normal force times our distance. All right. Now, we've got to figure out what this normal force is in order for us to continue with the calculation. The normal force in this problem is not the same as the normal force was over here for our problem when we're just pulling on the box horizontally. Okay, because we're pulling now at an angle, that changes actually our normal force, okay? So we can figure out what is that change in the normal force. Just like we did over here to find what the normal force was, we use Newton's second law in the vertical direction. We do it over here too, okay? So let's do Newton's second law in the vertical direction. Remember, we're not accelerating in the vertical direction, so this is 0. So 0 equals, what are all of our forces in the vertical direction? We've got the normal force upward. We've got a vertical component of our applied force. Okay, so if I come over here, the vertical component of my applied force is going to be this little bit that I kind of drew in with the squiggly mark here, okay? So this side, let's call it PHY applied, okay, is opposite of our angle theta here. So this is a right angle triangle. If we use sine of theta, this angle equals my y component of the applied force over the hypotenuse here, which is the magnitude of my applied force. So this applied force in the vertical direction, because I'm pulling at some angle above the horizontal, is equal to the magnitude of my applied force times sine theta this time. Okay, so we've got our normal force plus this vertical component of our applied force, which is F applied sine theta, and then we have the mass times gravity pointing down. So then we'll say minus mg. Okay, so the normal force for this problem is much more complicated than the normal force was over here for our first problem. Okay, so if we solve this for the normal force is equal to mass times gravity. I'm going to move this quantity to the other side of my equal sign, minus the applied force sine theta. Okay, this theta here, that's my angle 30 degrees. Okay, so then this is equal to minus coefficient of kinetic friction times mass times gravity minus our applied force sine theta times the distance that we pull. Okay, so equals minus 0.2 times 50 kilograms times 9.8 meters per second squared minus, running out of room here, minus 120 newtons, which was my applied force, sine of my angle 30 degrees, at which we're pulling above the horizontal, okay, and then times my 5 meters over which this force is applied, okay? So then my work done by friction, plug in all this bit, is minus 430 joules, okay? So this time, our work done by friction is actually a little bit less than the work done by friction in our previous problem. Why is it a little bit less over here? Because we've got that string, that rope that's pulling upward, okay? And it's removing some of that weight component that's of that crate that's resting on that surface. So no longer will the normal force be equal to the mass times gravity. The normal force will actually be a little bit smaller in proportion to the force that we're applying vertically as we're dragging our object across the surface. So that's why the work done by friction is a little bit less, because it all has to do with that normal force, since our friction force is also dependent on the normal force, okay? So if we've got our work done by friction, let's figure out the work that we do total, our net work. So the net work, as we already saw, is going to equal the work done by friction plus the work done by our applied force, okay? So our work done by friction, we had just calculated it, minus 430 joules, plus our applied work from the applied force at the angle. And so that's going to be our force applied times the distance over which we pull times cosine theta, where this angle, theta, is the angle between our direction of motion and the angle at which our force is applied. And in this case, that angle is 30 degrees, okay? So this is minus 430 joules plus my applied force, 120 newtons, times 5 meters, times cosine of 30 degrees. And then that is equal to a total of 89.6 joules. Okay, so the net work that we do, the work that we do to move the object horizontally across the surface is equal to 89.6 joules. Okay, and we see that it's actually also a little bit less than the net work that we had in our original problem over here. Why? Again, that's all because we're pulling with an applied force at some angle above the horizontal. And whenever you do that, you can reduce the amount of work that friction does as we're dragging the object horizontally. And we also reduce the amount of work total, the net work in our system to move our object horizontally.